Hello everyone. Here I'm Professor Itkarkar, giving you a presentation on or a video on a practical on a direct sequence code division multiple access. That is, we call it as DS-CDMA technology, right? So it's CDMA stands for your code division multiple access. So we'll be seeing how we are going to perform in practical on this code division multiple access. So before starting with the practical, we'll just go through what is a direct sequence, that is code division multiple access, right? So CDMA is what we call it as a code division multiple access technology, which is a multiplexing technique which occupies the various users in a single transmission channel. So what you can say is a single bandwidth is nothing but utilized by a multiple user, and hence we call it as the bandwidth optimization, which has been done by using, that is, code division multiple access. Now in CDMA, it uses the UHF frequency, that is ultra high frequency for transmission, and its basic application is nothing but a cellular telephone system. So the band at which it works for the cellular telephone, it is 1800 megahertz to 1900 megahertz, or we can say 1.9 gigahertz frequency itself. Now there are actually, when we say it's a code division multiplexing technique, it is a code which has been used by a different users. So it's code which does matter, and this code is nothing but what we call it as a spreading code which has been used as, right? Now CDMA, as I said, it is a code which has been generated. It is called as a Walsh code which has been generated. So there are different Walsh codes which are being generated for different users which has been there. And hence we can say that there are approximately 61, that is, users which are accommodated in that is a carrier frequency or a channel bandwidth of 1.22 megahertz bandwidth itself, in which the data is being transmitted, and it has been transmitted on two different PN sequence codes itself. Now, what do you mean by PN sequence? It is a pseudo-random code which has been generated, and that code is nothing but acting as a unique code, which is that is a security code for the this multiplexing technique. So the best advantage of CDMA technology is your data is nothing but kept secure, and the security is maintained, but the bandwidth is increased. But what we have is the main advantage of what you can say is CDMA technology. Security is there with your data. This is the basic difference between the GSM technology and a CDMA technology, right? Now, there are two types of, or we can say two ways in which your CDMA is nothing but that is implemented. One is called as a direct sequence, or we call it as a direct sequencing, and the second one is nothing but a frequency hopping technique. The first one is the practical which we are going to go through, which is a direct sequencing technique used by. So this is a block schematic of your that is direct sequence CDMA technology. What you can see is the input signal, that is your voice data, is being that is added, or we can say it's logically added with your code data. So it is a code generator, or we call it as a PN sequence generator. PN sequence generator is nothing but generated logically. So every PN sequence is nothing but a unique code which has been generated and added with your data. So whoever knows the PN sequence can access or retrieve your information signal back again. So if PN sequence is not known, then the data cannot be accessed. So this PN sequence is nothing but acting as a security code for your data which has been transmitted, right? So this signal is nothing but what we call it as the coded sequence which has been there, right? What we call it as the coded sequence. Now this coded data, that is, instead of input data, now it is added with the, what you can say is the security code, or we call it as a PN sequence code. And then it has been modulated by using a digital modulation technique. So the digital modulation technique used can be a binary phase shifting technique, can be a binary frequency shifting technique, it can be a quadrature phase shifting technique, or it can be also GMSK, that is Gaussian minimum shifting technique, which is used in cellular transmission, right? So it has been modulated on a high frequency carrier and then transmitted. We'll see the process, which is nothing but reverse at the receiver, where the signal, incoming signal, is first amplified, demodulated. And what you can see is the PN sequence is once again logically added with the demodulated signal. And then actual the data is nothing but recovered. So if you know the PN sequence at the receiver, then and then only you can retrieve the data. If you are not aware with this particular security code, then we cannot retrieve this data. So this is the beauty of what you can say CDMA technology, or you can say advantage of CDMA. That is, if the PN sequence of the security data is known, then and then only we can retrieve the data. Though you can say the disadvantages, bandwidth required is very high, but the advantage that is you can say is the security is maintained with the data transmission, right? Here we can see an example of a PSK signal which has been shown, which has been that is modulated by using a PN sequence. So what you can see, the first waveform that is in red color, it's nothing but your digital data. So my data is 1 and 0. And the second signal which is shown in yellow is nothing but a PN sequence. So the PN sequence is, see what is the data? It is 1. Here I can see 2 bits together. So it's 0, 0. Then it's again 1, 1. So my data which I can read is 1, 0, 0, 1, 1, 0, 1, 0 and 1, 1. So this is the data, which is logically added with whom? That is the PN sequence is added logically with whom? Data. Usually it is a XNORing of the data which has been done. That is XNORing which has been carried out between the data and what we call it as the PN sequence. So you can see this is the coded output, that is the spreaded signal which has been represented by what we call it as, that is the green color. So this is the XNORing of the data. And the third signal is your modulated signal which has been, that is BPSK. So wherever you can see a transition in the spreaded data, that is the coded data, there is a phase shift which has been created. See, you can see a full cycle over here. Again, there is a transition that is from 0, the data is being gone to 1. And hence there is a transition which represents that there is a phase shift which has been created. Once again, we can see here the continuous RF signal, and what you can see is again the change in phase shift. Once again, the transition takes place over here, change in phase shift, change in phase shift. So this is 180-degree phase shift which is shown in the signal. So that is a binary phase shifting technique, right? What you have is the second type of modulation is what we call it as the frequency hop CDMA technology, right? Now, what is this frequency hop technology is here? The band of the channel bandwidth is being utilized by many users in different time slots which has been there. And that is nothing but what we call it as a frequency hopping. In frequency hopping, basically what is done is the frequency synthesizer is nothing but that is added, logically added with your modulated data, and then it has been transmitted. The reverse happens at the receiver end. That is the synthesized data once again filtered and then demodulated. So you should know the frequency, that is the synthesized frequency at the receiver, which can be demodulated by using frequency hop. So here again, you have a frequency that is a PN sequence which has been transmitted and been utilized for different users on different frequency components which has been there, right? And hence that it has been transmitted in that way. So this is what you can say is CDMA technology. Now this is what we call it as the multiple users, that is CDMA, or we'll say a direct sequence CDMA signals are being modulated by using a PSK modulator. So there are 3 users which has been shown. What we can see especially here is every user has a different code which has been here. So you have a code generator 1, a code generator 2, and a code generator 3. So every user is nothing but using a we'll say a unique PN sequence which has been there. So your data is going to be kept secure as the PN sequence generated or the security code generated is nothing but a unique code. And then it has been transmitted on a single carrier, that is 1.22 megahertz carrier that has been used in CDMA. Now basically CDMA, that is what we have, the technique which we have seen is this direct sequence spread spectrum technique. Now this will say CDMA is nothing but what we apply in cellular telephone system. That is in cellular network, we are applying this, that is CDMA technology. And hence this is the basic difference between CDMA and GSM. That is why CDMA is being giving you security for your data transmitted, while GSM technology is directly modulated by using that is QPSK, QPSK, or we say that is GMSK, right? So what are we going to see is we are going to see next the experiment, that is an experimental setup for direct sequence CDMA technology. So we'll go through the sequence. We'll now shift to the laboratory setup for CDMA technology. Hello all. Today we are here to explain the experimental setup on DSS coherent PSK, which we usually call it as a DSS PSK modulator. Now we'll start with what is DSS. Now DSS stands for Direct Sequence Spread Spectrum PSK. Now here it is written as DSS coherent PSK. So coherent stands that it is a receiver which is going to be coherent. That is a carrier and a transmitter, and the carrier and the receiver are dependent on each other, and hence we call it as a coherent. Now before starting with the actual setup, we'll see what the blocks schematics which are being used over here, or the circuit blocks which are being used. So you have an 8-bit PN sequence generator. I'll tell you what is a PN sequence generator. Then there is a pattern generator, that is a bit pattern generator, that is your digital data generator. Then there is a logic transmultiplier which is used, which is a XNOR, that is a multiplication which has been done. Then this is your multiplier, that is 1496 is the IC which is used as a multiplier IC, that is a PSK generator. Then this is again in 1496 squaring circuit which has been used. I will tell you what is the functions of each and every block. This is a band pass filter which is tuned to twice omega c. This is a frequency divided by 2. Then this is your receiver circuit, that is a receiver demodulator. It's a low pass filter and a comparator circuit, and once again it's a multiplier circuit, and then your detected output. So your original pattern, that is original bit which has been generated, and this detected bit which has been generated should be one and the same. So this is, you can say till here it is the modulator part, and this part gives you the demodulator part. So you can say 1, 2, 3, 4, these are the modulator blocks, while demodulator is rather, this is the demodulator section, but this is again a recovery circuit, carrier recovery circuit which is used as the demodulator. So it's at the demodulator itself. So this block and this block, these that is comprise the demodulator section which is going to be there. Now starting with what is first DSS PSK. Now direct sequence spread spectrum. Direct sequence stands for, that is a direct multiplication of the bit sequence with the PN sequence which we are using. Now the bit sequence, as I said, it is nothing but a digital data generator, because this is a digital modulation technique. We need the data, it is in the form of digital, correct? Now what is a PN sequence? It is called as a pseudo-random sequence generator. What do you mean by pseudo-random sequence generator? It is a random generator which has been used. So it's a 8-bit random generator. So it's, the sequence is going to be repeated after, that is 256 bits which is going to be there. So it is 2 raised to 8 minus 1. So that is, after that the sequence gets repeated. Now it's a random sequence which has been generated. As I said, it is repeated after 256 bits. So it's random, and hence the security of the data is going to be maintained by using this PN sequence. Means if I add this particular PN sequence with my pattern, then those people or those receiver who knows the PN sequence can regenerate your, that is a data back again. So it's acting as a security code for the data which you are transmitting, right? So there is a technique where we have a 6-bit, 4-bit, 8-bit pattern generator. We have a different practical setup for this also, for generation of 8-bit. So just remember that this is a security code for keeping your data secure, that is transmitting the data in a secured way. That is your digital data with the help of the PN sequence is going to be transmitted. Now how it is done is, see, here you have a transmultiplier, that is an XNOR IC which has been used. So you give one input as the PN sequence, the other as the bit pattern, and the XNOR, that is a logical output, is nothing but your, that is the mixing of two signals, or we'll call it as the secure data which has been, that is generated. This is again a PSK modulator which is a multiplier, that is bit pattern multiplied by the carrier, B of t multiplied by sin omega ct. So you have, for example, this is your bit pattern, this is the PN sequence. So if I name this as BT, this as BT dash, BT and BT dash will generate some B double dash which has been there. This B double dash will go as an input to it. So if B double dash is 1, there is no phase shift. If B double dash is 0, then there is a phase shift of 180 degree which has been created at the, that is a modulator output, correct? Now as I said that it is a direct sequence, it is a multiplication. Now why do we call it as a spread spectrum? Now spread spectrum is, see, if I directly only multiply the bit pattern by the carrier. So for example, my bit pattern is of a frequency that is 1K. So your spectrum, that is PSK. So it is, if you go through the frequency spectrum of PSK,
you'll see that the center frequency is Fc, and the lobes which have been created on both ends, it is Fc plus Fb. So Fb is nothing but, as I said, it is 1k frequency. Fc, for example, is 20k. So 20k plus 1k, that is 21k on the positive side, and 20 minus 1k, that is 19k on the other side. So the difference frequency is nothing but the spectrum which has been occupied for transmitting the modulated signal, that is a digital data. But now what are you doing is, you are transmitting it with the help of a PN sequence. So if I say that PN sequence frequency is now 2k. So 2k which has been added with whom, that is 1k. Now why I am adding the frequency? Actually it is nothing but multiply, but it is a multiplication in time domain. So multiplication in time domain becomes convolution in frequency domain. And in convolution we know that we add to frequency component. So it is 1k plus 3k which has been added. So if I give this 3k as an input over here, and the carrier, as I said, that is going to be 20k. So 20k carrier plus FB, now it is 3k. So it is FC plus FB. So it is 20 plus 3, that it is going to be 23k. So your spectrum gets increased. With only 1k, the spectrum was extended up to 21k. But when I consider PN sequence and the bit pattern, the spectrum increased was nothing but 23k. So your spectrum is increased. But why the spectrum increases means bandwidth increases. But this is a disadvantage in communication system, because if you are increasing the bandwidth, the number of users are going to reduce, correct? But what is the advantage with DSS PSK, that is spread spectrum, is the security in the data is going to be maintained by using, that is, a spread spectrum technology. Though spectrum utilized is more, but security is going to be there in the data transmitted. So we'll see one by one the block. The first thing which I have done is nothing but connected the ground of one of the CRO probe. Now we'll go to the CRO probe, that is we are going to observe the PN sequence output which has been generated, correct? So before that, if we'll start with the pattern generator, that's going to be better. So I have a pattern generator, that is a pattern which has been generated. So I have used a second pattern generator, that is second bit which has been generated. We'll just see this pattern on the CRO, how it has been generated. So this is your pattern which has been generated, correct? So once again, what is the pattern? It is 1 0 1 and 00 is the pattern which has been generated, which is again repeated. 1 0 1 00 is the pattern. So this is your pattern which has been generated. I'll put again the DSO in the run mode. Now we'll once again come to our kit. I'll just show you what is the PN sequence which has been generated. So we have a PN sequence. So I'll just connect it to the PN sequence output now. Okay, we are just observing only the waveforms now. Now come to the CRO. See here, the second channel is nothing but the PN sequence which has been generated. So as I said that is the frequency of pattern is going to be less, and the frequency of that is your PN sequence is high. See the time period, and hence time is less, frequency is going to be more. So you can just see that in one that is a PN sequence, that is 1 bit duration. If you observe this, that is in 1 bit duration, there are multiple PN sequences which are being generated. Example, if I observe here, this is 1 bit which is there for the that is your data bit, but in that data bit you have 1 1 0 0 1 1 1 0 0 0 1 and 0. So this is the that is the PN sequence. So in 1 bit pattern, there are multiple PN sequences which are being generated, right? So now what is going to be done? See, once again I'll just expand it, put it in the run mode, and once again I'll just make it stop, or rather once again time period is reduced, and you can see that both the that is a pattern generator and the PN sequence together. So you can see in one pattern there are multiple PN sequences which are being generated, right? Now come to the next. So now we'll see the multiplier, that is a transmultiplier output. Now for the transmultiplier output, I'll be connecting now the PN sequence as an input to the transmultiplier block. So here this is a point where the PN sequence is connected, and then the pattern generator, that is the bit pattern, will be connected to the point, that is the pattern point. So I'll just connect this as an input over here. And now the transmultiplier output. So I'll show you how is the transmultiplier output. So once again it's been connected. We'll see with respect to pattern generator, that is pattern, how is the transmultiplier output. Or you can also see it with respect to the bit pattern itself, the PN sequence itself. So we'll just see how the output is going to be for the transmultiplier. So see here, the transmultiplier output, is the second, and the first one is your PN sequence. So both are right same. You can see that it's the data bit, or we'll say it's a XNOR, and hence it is a reverse which has been there. So one is your PN sequence, and the other is nothing but the that is a transmultiplier output, XNORing of the data which has been done over here, correct? So now we'll come to the next step, that is apply this transmultiplier output, which is now acting as a bit pattern or the data pattern for the modulator, right? So we'll see that this is the output of the modulator which has been there. This is 1496 IC which has been used. Now what I'll be connecting is, now this will be acting as a bit pattern. What bit pattern? That is a transmultiplier output. The point is over here, that is I'm giving as an input. Now the carrier is internally connected, so no need to connect the carrier. Otherwise you can just observe how the carrier has been there. So we'll see the carrier. Now here it's the carrier, and we'll see the PN sequence, we'll see the output of that is a transmultiplier. So you have a transmultiplier and carrier which I have connected both together. So I'll just see, we'll observe this output on the, that is the DSO. So this is your transmultiplier and the carrier output. So your carrier is a sinusoidal carrier, and the transmultiplier output which has been seen on the DSO. So this is your transmultiplier output. I'll just show you once again the PNC, that is a transmultiplier output, and this is your carrier. So this is the waveform which is being observed, correct? Transmultiplier and the carrier. Now the frequency is very high for this, hence it's not observable. It's approximately, I'll say that we need to measure. So if you want to measure the frequency of the second channel, we'll measure the frequency. So it's going to be measured. One minute. So it's measure. So it's channel 2 which you are measuring, and hence I have kept it as channel 2 only. And the frequency will say channel 2, type, minimum, max, rise time, fall time, width. So frequency is 19.7. As I said, it's approximately 20K is the frequency of carrier, correct? So we'll see now the next step, that is the modulator output. Now I'll be showing you the modulator with respect to transmultiplier, that is a shift which has been created in the transmultiplier. So I'm just removing the point connection of the CRO from the carrier and now connecting it to the modulator output. So I have connected it as an input to whom? That is the modulator. Now once again I'll just auto set this DSO. Now come here. So this is your phase shifted output, which is the second phase shifted output. You can see that is the channel, second channel. If you want to observe the phase shift, I'll show you how the phase shift is. See, when there is a transition which is taking place, there is a phase shift which has been created, right? Where there is a transition taking place, there is a phase shift which has been created. Once again, I'll just put it in the run mode. We'll see, I'll show you a multiple phase shifts which are being created in this. So you can see that ultimately there is a break in the waveform for every transitions you can see, right? So if I expand this, you can see the phase shift which has been created. So every transition there is a phase shift which has been created in the PSK output. So it's a 180-degree phase shift which has been created, which you can just observe it, right? So this is the phase shift, that is a transition which has been taking place. So this is a phase shift which has been created. So this is your PSK output which has been wirelessly transmitted in the air, where you can transmit any digital data, that is through this particular thing. Once again, this is your transition and this is a phase shift which has been created, right? So next is coming to the receiver side. Now when we come to the receiver side, we need to first recover the carrier. So there is a carrier recovery circuit over here. Now how is the carrier recovery circuit used as say? Now the data output is nothing but, or we'll say modulator output is bit pattern multiplied by the carrier, but it's nothing but the transmultiplier output. Though it is the addition of two frequency component, it is going to be one single frequency component, and that is a digital data which we have observed already. So that is a transmultiplier output. and that transmultiplier output is multiplied by the carrier. So it's B of t will say sine omega ct, which has been there. It is B of t sine omega ct. Now what you need is, for the recovery, you are going to recover the carrier from the transmitted, that is the modulated output or the transmitted signal. So which is your transmitted signal? This is your transmitted BPSK signal, or we call it as the PSK signal, binary phase shifting, that is the signal itself. I have given this as an input to this particular squaring circuit input. Now if I say, if I am giving as an input to this particular squaring circuit, it is going to square the component. It is sine component which is there, B of t sine. So it's going to B square sine square omega ct, which has been done. So sine square is nothing but, that is, we'll say 2 sine square, which has been done, and that is nothing but what we call it as 1 minus, that is cos 2 alpha, or we'll say cos 2 theta or cos omega ct, which has been there. So here you are getting a component that is 2 cos omega ct. It's a trigonometric that is operation which we can see. It's a so you have here sine square will be getting here, it is as 1 plus cos 2 omega ct. So you have, when you pass it to the band pass filter, the 1 plus, that is first component, which is a constant, that is DC component, that is 1, will be attenuated by the filter, and only the cos 2 omega ct component will be there at the output of the band pass filter. So here at the band pass filter, you are going to get twice as the carrier component. Once again, if you want to check it, check the carrier frequency. Here it is 20k, and here it should be 40k. So if you want to check, we can check the that is the carrier frequency itself. So I'm connecting the carrier and I'm connecting the band pass filter together. Correct? So band pass filter, I'll just check which the channel, where the channel is, which channel it is being connected, and then we'll just check it. That is, I'm connecting the one as the carrier and the second as the that is the band pass filter output, which is going to be twice the carrier component, right? So once again, I'll just okay, right, that we'll see later. Now what you can see is this is band pass filter output, right? And correct. So this is your band pass filter output, which is twice omega ct. It is divided by 2 now. Okay, it is divided by 2. So here I get once again my carrier back again, that is omega ct. So what you have done is, at the receiver end, you have generated the carrier back again from the transmitted carrier, by using this particular circuit, that is, we call it as a carrier recovery circuit. Now what you need to do next is, you need to connect, now this is your actual receiver, so now you need to connect the carrier, okay, carrier which is used for recovery, as one input to the that is a demodulator. The second input to the demodulator is going to be the transmitted output, that is a modulated output. So I'm connecting the modulated output as a second input to this particular that is the demodulator. It is passed through a low pass filter and compared, and then once again given to a block, where you'll now get here the transmultiplier output. Okay, you'll get a transmultiplier output. Now to recover back our original signal, I need once again, that is the PN sequence, to be given at the receiver. So if PN sequence is known at the receiver end, then and only then the data can be recovered. Otherwise, the data cannot be recovered. So what I am doing is, once again I am giving the that is transmultiplier output, which has been recovered at the receiver end, as a second input to this particular receiver multiplier circuit. And you once again need to connect the PN sequence, which was originally generated as an input here. So here we are giving from the kit provision, that is the original PN sequence itself, but rather at the receiver end, you need to regenerate this particular PN sequence. So those who have transmitted the PN sequence, they know the circuit for PN sequence. You should, that is same circuit should be generated at the receiver end to generate the, that is a PN sequence back again. Now once again we'll see the recovered data and the transmitted data together. So this is your recovered digital data which is going to be there, and then I'll see the transmitted data which has been there. So this is your transmitted data which has been connected now to the channel 1, and the recovered data to the channel 2. So this is your original bit pattern which has been there, that is, we have used the original bit pattern over here, and this as the recovered data, this as the recovered data. Now we'll see both together on the DSO whether both are, we are getting it as the same. So once again, just I'll go to the auto set option and just we'll check it on the DSO whether we are getting it same. So what you can see is no, both are not same. Why both are not same? Because the filter which has been designed over here is not exactly tuned to twice omega c. So you need to adjust the filter in such a way that the recovered signal is going to be that is same. Okay, the recovered signal is going to be same. So I'm adjusting both. See here, I'm adjusting the carrier and that is the recovered data is changing. Are you getting? So what are we doing is we are adjusting the filter, that is the frequency, right? What I'm doing is I'm adjusting the filter frequency from here. So I just have adjusted in such a way that you need a fine adjustment again here. Okay, you need a fine adjustment which has to be done, and we'll see that yes, the recovered pattern you can see is same. As you can see, it's 10100, the same, it's 10100 is the pattern which has been received at the receiver end. So this is the data transmitted and the received data which is going to be one and the same. So we have gone through the full experimental setup. Once again, just see the connections, or just do remember the connections which are been there. So PN sequence multiplier, that is bit sequence multiplied output given to again in 196, carrier multiplied by the bit pattern, then the recovery circuit, demodulator, and the received circuit. So this is all about the experiment on DSS PSK, that is coherent PSK. Thank you all listening patiently. If you like the video, please do like it and also subscribe my channel. Thank you.